All right, we are looking at rhombuses and squares, or you can say rhombi and squares as well, for 5.07, our exit ticket lesson. So a rhombus is a quadrilateral with four congruent sides, and the opposite sides are parallel. So that would indicate that it's, of course, a parallelogram, which also means that any properties we've discussed about parallelograms apply to the rhombus. Now remember, a quadrilateral is any four-sided figure. So you can think of other four-sided figures besides a rhombus as well. We've got rectangles, of course, we've got squares, of course, and those are the two other parallelograms. But we also have things like trapezoids and kites. So trapezoids and kites would be two different types of quadrilaterals that would exist outside of this little circle diagram that we have here, outside of the red circle, that is. Okay, so as an example, I just wrote trapezoid out there because it's not necessarily, of course, related to a parallelogram. And so here we have a rhombus that belongs to the family of quadrilaterals. A rhombus belongs really to the family of parallelograms. So let's look at some of the properties that it possesses. We know that it has four congruent sides, and we know the opposite sides, of course, because it's a parallelogram, are parallel. So here all four sides are actually congruent to each other. They're all the exact same length, which of course indicates the opposite sides are congruent, but all the sides are congruent. And we have opposite sides are parallel, which is what a parallelogram is supposed to indicate. Opposite sides of a parallelogram are parallel by definition. So there's a lot of properties involved with a rhombus. Several of these properties are actually properties of parallelograms. So we have opposite sides are congruent, opposite angles are congruent, consecutive angles are supplementary, and the diagonals bisect each other. All four of those represent properties of parallelograms. So every other parallelogram that we talk about is going to have those exact same properties as well. So we've kind of outlined that here in this particular order. We start with this one first. Opposite sides are congruent. Those are just examples written down of congruent statements. So in this case, it's not only just that the opposite sides are congruent, but that all of the sides are actually congruent to each other as well. That is a property of a rhombus. They are all going to be the same exact length. The opposite angles are going to be congruent as well. That doesn't mean that all of the angles are the same. It just means that the opposite angles have to be congruent. That's the definition, or part of rather, a property of a parallelogram. So consecutive angles are going to be supplementary. So after the second one here is consecutive angles are going to be supplementary. That means that the sum of the consecutive angles like EF or EH or HG or F and G, those angles sums will equal 180 degrees because they're same side interior angles. You can think of this example set of parallel sides as two parallel lines cut by a transversal, and that makes these angles same side interior angles. So they're going to be supplementary because of that. Then of course we have the diagonals bisect each other. Now the word bisect means to cut in half, right? So if you have a segment like E to G, that is broken up into EJ and JG, as is demonstrated there. And that means those two lengths are going to be the same. Likewise, we have H to J. That's going to equal J to F. Those are also bisected and cut in half as well. So that means that you have two equal halves apiece, in other words. Then we have perpendicular diagonals. So the diagonals are also going to be perpendicular. So that means that they all meet at a 90-degree angle. Right here in the center. 90 degrees there, 90 degrees all the way around. So when we talk about the diagonals being perpendicular, that is a special property of rhombuses or rhombi. Okay, that is unique to the rhombus. And then as a result of it being a part of a rhombus, it's also going to be a part of a square. And then lastly, the diagonals bisect the angles. That is another property that is unique to the rhombus as well. The angles are going to be bisected. That means to be cut in half. What does that indicate? Well, that just means if I zoom in on one angle pair as an example, this angle right here will be the same as this angle right here. This angle right here will also equal this angle right here. And that means the other side as well. That's angle bisection, and a rhombus has that property as well. So as you can see, there's a lot of properties here with a rhombus. So I would highly encourage you to use that as a reference when you are going through problems involving a rhombus. Let's go ahead and practice a problem now. We want to know whether this is a rhombus, or rather in the rhombus, we want to determine the length of QR and the measure of those angles. So we'll start with the length of QR. So QR right here is going to represent this side length of the rhombus. We recall that all sides are congruent. Since all sides are congruent, we know, and I'll just use the symbol for congruence, that QR is going to be 50 units. And that is because one of the side lengths was 50, so all of the side lengths have to be 50. Next, we're going to find the measure of PTS, so the angle PTS. That angle is located P to T to S. So T is the vertex, that means right there. This is the center of the rhombus, where the diagonals intersect, I should say. And we know that a property unique to them is that they are perpendicular, right? So because the diagonals are perpendicular, again, that's what this symbol means. Because the diagonals are perpendicular, the degree value of that angle is 90 degrees. Lastly, we are looking for the measure of RSQ, the angle RSQ. So to find the measure of that angle, we can see that R to S to Q is represented by this angle here. And remember that another property of parallelograms is that, or of rhombuses I should say, is that their diagonals bisect the angles, right? So the diagonals bisect the angles. And remember that that means cut into equal halves. That's what the word bisect means. So if this is 55 degrees, then that also is 55 degrees as well. So we have 55 degree angle, a 55 degree angle for that particular value. So what I would do is pause the video and see if you can come up with the length, or the length of Vx, that is, and the measure of angle VXW. So recall that the diagonals bisect each other, so we know that we're looking for V to X, and we know that the other side is 3.98. So because the diagonals are bisected, this length is equivalent to that length. Therefore, it is also 3.98, so that should have been your answer. That is because the diagonals bisect each other. For the measure of angle VXW, we are now looking at the angle value really at the center here, which I'll highlight in blue. The diagonals are perpendicular. That means that they're 90 degrees. So we should say 90 degrees. The diagonals are perpendicular. So the diagonals bisect and the diagonals are perpendicular, and that is how we know those are the answers to that question. Now let's take a look at the square. Now the square is an almighty quadrilateral because, as you can see, it's a smaller circle. It's concentric, meaning that it's kind of completely have the same exact center as the other circles. It's contained within. That means that all the properties of a rhombus and all the properties of a quadrilateral a square possesses, right? So a square is going to be a parallelogram. It's going to contain the properties of both a rectangle and a rhombus and all the properties of a quadrilateral. So it has 4 congruent sides, 4 right angles, and the opposite sides, of course, are parallel. What's unique about it is that it has 4 right angles as well. And as you already know, quadrilaterals have 4 sides. So we can see there that we have the right angles. All 4 sides are going to be the same. And of course, because they're right angles, the degrees of those angles are 90 degrees. So let's take a look at the properties of a square. It possesses all of the properties of a rhombus. However, there is an additional property that has been added, right? So all of these others, for example, I'll just point them out. These are the properties of a parallelogram. These are the properties of the rhombus. And here's a unique one. This one right here, the one in blue. This is new. That is a property that is introduced because it is also a square. So all of those original expressions and original labels that I put on that original figure are the same, except the new one is at the very end here, right here. The diagonals are congruent. That means that when you see the diagonals bisecting each other like so, they're all broken up into those 4 equal pieces. Each diagonal is exactly congruent to the next. They do meet at a 90-degree angle. The angles are bisected as well. The angles are all going to be bisected, so each of those will be 45-degree angles because together they add up to 90, so they're all the same. All 4 sides are the same as well. And of course, as you know, because it's a parallelogram, the opposite sides are going to be parallel, which is exactly what it should be. So again, this has the most properties out of all of the parallelograms in particular. So let's take a look at an example. We want to, in the square, determine the measure of angle ADB. So the measure of angle ADB, let's highlight that. A to D to B is this angle actually right here. The D is slightly cut off. All right. So we know that the diagonals are going to be bisecting the angles. So if the entire angle is 90 degrees, that means each of these halves is a 45-degree angle. So the measure of this angle is going to be 45 degrees. Again, the reason for that is because the angles are going to be 90 degrees each, and they're all being bisected by the diagonals. So that's why each of those represents 45-degree angles. 45-degree angles. Now, for part B, we're looking for the measure of a segment B to E. So B to E is this segment right here. We are told that this segment is 2, which means that all of the others are also going to be 2. So BE is equal to 2. The diagonals are congruent and they bisect each other as well. So that means that all 4 of these subsets of the diagonals, the 2 subsets each of each diagonal, are congruent to each other, so their lengths are the same. And then lastly, we have to figure out the length of B to C. So I want you to focus for a moment on that. We have this right triangle. We know this is a right angle. We know that this is 2. We know that this is 2. We know that that is a right angle there. That's where the right triangle is. So this is going to be a right triangle, and we're looking for the length of B to C. There are several ways that you can actually figure out what the length of B to C is, but perhaps the most prudent way to figure that out is to utilize what we refer to as the Pythagorean theorem, right? Now, there are other ways that you'll see later on, especially in the second semester, that we will explore, but the Pythagorean theorem is a go-to for this. You're looking for this length, which we'll just go ahead and call B to C, right? So we have 2 squared plus 2 squared. Leg squared plus leg squared equals hypotenuse squared. So here we have 4 plus 4 equal to BC squared. That's the length, of course. And that gets us, in this case, 8. And we're going to take the square root of 8 to get the length of BC. And the exact length of BC is the square root of 8 units. However, we can also approximate that as 2.83 units for the length of BC. So I'm just using the Pythagorean theorem as an example to find that specific length in that right triangle. In the future, you'll find that technically Each of these will be 2 square root of 2, and there's a really easy and nice way to verify why it's 2 times the square root of 2. And it has to deal with the types of triangles, right triangles that you're dealing with. But if you did Pythagorean theorem, 2 square root of 2 is 2.83, or the square root of 8. So just letting you guys know that that is exactly what those lengths are going to be. Okay, so why don't you go ahead, pause the video, and see if you can come up with the measure of GJH, GHJ, and the length of JG. Alright, so the angle GJH is here, so that's 90 degrees. The measure of GHJ, that is the angle down here. We know that's a 45-degree angle. And for the length of J and J to G, which is the segment length here, we know that we're missing this length, which we'll go ahead and call X and X. We want J to G specifically. So we know that X squared plus X squared is equal to 6 squared, because remember, this is the right triangle that I'm looking at where the hypotenuse is 6. So we have 2 times X squared equal to 36. We can divide both sides by 2 to get 18. And by taking the square root of 18, we can get our approximate answer, and that's going to be 4.24 units. So therefore, our answer needs to be 4.24. Now, determining the quadrilateral, right? So we want to select all of the possible answers available when we're dealing with what type of property we're working with here and what type of figure we want. So opposite angles are congruent. That is true for rhombuses and for squares. Consecutive angles are supplementary is also true for both. Then we have has 4 right angles. Only a square has that. In fact, I'm going to use a different color for that. I'm going to use orange for that one. Opposite sides are parallel, that's true for both. Opposite sides are congruent, that's true for both. Has 4 congruent sides, that's also true for both as well. So the only one that was unique was the has 4 right angles. Only the square has that when you compare it to the rhombus. So why don't you guys go ahead and try this. Select all the answers that are correct. So in this case, diagonals bisect each other, are congruent, are perpendicular, and bisect opposite angles. So what you should have said is that the diagonals bisect each other for both. Diagonals are congruent is only true for the square. Diagonals are perpendicular for both. And diagonals bisect opposite angles. That is also true for both as well. So again, only the diagonals are congruent in a square rather than in a rhombus. Now, I'm not going to actually go through the graphing process here because I already have a video in our playlist or in our YouTube channel that demonstrates exactly how to do this, and I would encourage you to refer to that video to see how you can actually take a set of ordered pairs and plot them to see what's going on with your figure. What we're going to do is take a look at the coordinate plane and kind of examine an example of, well, let's just take a look at it. In this case, the quadrilateral in question. We want to examine what type it actually is. So what we really want to do is we want to figure out what type of properties it actually has to classify that quadrilateral. So when we look at the figure right there, we can see that if you look at the slopes, first and foremost, it goes up 1 and then it goes over 3. So it has a slope of 1/3. As does that side as well. And this one goes down 1 and 3 to the right, so it has a slope of -1/3 instead. So because they have opposite sides with the same slopes, those are opposite sides that are parallel, right? So opposite sides parallel or are parallel. That's important because you're establishing that it's a parallelogram. So all I did was I did my rise over my run, right? I went up and I went over. So up 1 over 1 was positive 1/3, but down 1, 3 to the right was negative 1/3. So that's going to be the slopes of those particular segments, and I verified that their slopes are positive 1/3 and negative 1/3, and so that's why opposite sides are parallel. But moreover than that, you can actually show that the opposite sides are congruent to each other as well. For example, you can go up 1 and you can go 3 to the right, up 1 and 3 to the right. That forms a right triangle. And with that in mind, you could do Pythagorean theorem to verify the length of AB, but you already know intuitively that it will in fact be the same length, because look at this. It goes up 1 and over 3 as well, so it too is also going to have the exact same length, right? So 1 squared plus 3 squared is equal to 10. So the length is going to be the square root of 10, because you have to take the square root of the hypotenuse or the square root of the hypotenuse squared to get the hypotenuse. 1 squared plus 3 squared is going to be square root of 10. And actually, what's really interesting about that, we could be a little bit more specific. You can do the distance formula as well, but I'm showing you a way in which you can think about using the right triangles, because it is in some ways faster to think of it visually, right? So 1, 3, 1, and 3. I'm showing an example of how you get 10, and you're trying to find this missing length of AB, right? So you would say 1 squared plus 3 squared equals AB squared, and that gets you 10 for AB squared, so that's why the square root of 10 is equal to AB. Well, that's also the same value for DC. It's the exact same setup. You have 1 and 3 for your right triangle. What's even more interesting is if you look at this right triangle, that's still technically 1 and 3. 1 and 3. Right? So the vertical change is 1, the horizontal change is 3, so you have a right triangle where you have 1 and 3. If you wanted to think of it in terms of negative 1 because you're going down, you can still do that, because if you have negative 1 and you square it, and you square 3, and let's say you get the length of AD squared as an example, well then you still get 10 for AD squared, and that means you still get the square root of 10 for AD. So therefore, because of that, we know that the length then of AD is going to be the square root of 10, just like AB was. And this, of course, will be the square root of 10. And likewise, this was 1 and 3 as well. So that means that you're going to get the square root of 10 for that side. So all four sides are congruent, right? So we have opposite sides are parallel and congruent. And then on top of that, we can also measure out what the angles are going to end up being as well. Now, we got to be a little careful about that, because when we're talking about angle measures, we want to be a little careful on what those measures actually are. Desmos can actually map out what those angle measures are going to be if you want to see that. There are certainly ways to verify that, but we know it's a parallelogram, and we know that the opposite sides are going to be congruent. That is a property of a rhombus, and that is what we need to show in that particular case. So there are other properties that you can test out as well, like for example, the angles are being opposite, of course, are going to be congruent to each other. These angles are going to be congruent to each other. But that's a property of parallelograms, right? So once I showed that the opposite sides are parallel, I already know the opposite angles are going to be congruent to each other. So I don't necessarily need to reference that. What I needed to show is that all four sides were the same, right? So once I've shown this information here, I know for certain that it definitely is going to be a rhombus. Now, given the diagram that I have and the figure that I have, because our angles aren't 90-degree angles, it's not a square, right? So as a result, we can certainly claim it to be a rhombus, because I've shown different properties that match what I should see for a rhombus. So you can go to Desmos and test out other features, and if you would like, certainly videos can be made to show exactly how you might determine the angles of the opposite sides using the Desmos program, or using a program like GeoGebra as well. So with that being said, we want to take a look at our exit ticket today. we have a rhombus that's stated as a rhombus, and they're giving us the measures of these angles, M and T, as well as the measure of O and T. So we want to be clear about this, right? Remember that it is a rhombus, and the measures of the angles M and T and O and T would be here and here. What property do you know applies to the diagonals and the opposing angles, and the diagonals and the angles? What do the diagonals do? Diagonals, the angles, right? What does that do? Refer back to the property slide, and then you'll understand that these measures have a certain special relationship to each other when you're trying to solve for the variable x. The second question is, it's a parallelogram with the given vertices. We're trying to particularly classify it. So you're trying to prove whether it's a rhombus, whether it's a rectangle, or a square. So if you're going to try to show that it's a rhombus, a rectangle, or a square, you got to show that it has all of these properties. I highly recommend that you use the Desmos graphing calculator when you're using this tool, so that way you can better understand how to classify a parallelogram when you're looking specifically at the figures below. Which of those is it going to end up actually being? And then the final one is, what's the measure of angle ABE in the square of ABCD? So ABE is going to be this angle right here. There's an example in our slides where we actually went through this very thing, and I would recommend that you go back and look at what that specific degree value was that we kept using when we were bisecting the overall angle at the end or vertex of a square. Okay, and so that's going to represent our lesson on 5.07 for a rhombus and a square.